All right, let's dive in. Today, we're pulling back the curtain on the invisible science that literally holds our world together, engineering mechanics. This is the secret rulebook that lets us build skyscrapers that touch the clouds, launch rockets into space, and design pretty much everything in between. So let's get into it. Just look at this thing. A massive crane lifting a ridiculously heavy load, and it's all just holding steady. How does that work? It's not magic, right? It's the precise, calculated application of engineering mechanics, the science that tells us exactly how forces and objects play with each other. So, what is mechanics, really? Well, in the simplest terms, it's the science of forces and motion. It's all about figuring out why things stay still, why they move, and what happens when you push or pull on something. For any engineer, this is ground zero. This is the foundation. Now, this huge field is pretty much split down the middle into two main parts. And for any engineering student, these are often the first two big courses you'll tackle: statics and dynamics. You can think of them as two sides of the very same coin. So what's the real difference? Well, statics is all about equilibrium. That means things are either perfectly still or maybe moving at a constant speed. It's the science of stability. Dynamics, on the other hand, well, that's where the action is. It deals with acceleration, things speeding up, slowing down, changing direction. One's about being stable, the other is all about change. And this is a perfect picture of the world of statics. This transmission tower, it's not going anywhere. It's been designed from the ground up to fight against forces like the wind and the heavy weight of the cables, and to just stay perfectly still. Every single push and pull on it is in perfect balance. Okay, to really get what's going on in mechanics, we have to learn the lingo. It's a language that's built on just a few fundamental concepts, and these are the absolute building blocks for every single calculation an engineer is going to make. Believe it or not, everything in mechanics really boils down to these four basic ideas. You've got length, which tells us about size and where things are. You've got time, which is obviously super important for dynamics. There's mass, which is a way to measure how much an object fights back against being moved. And then, the star of the whole show, force. We all know what a force is, right? It's just a push or a pull. But for an engineer, it's way more specific. To really know a force, you need three pieces of info, no exceptions. Its magnitude, how strong is it? Its direction, which way is it going? And its point of application, exactly where is it pushing or pulling? If you miss one of those, your whole calculation is going to be off. Now, to solve insanely complex problems, engineers have these really clever shortcuts, or idealizations. The first one is called a particle. Think about the Earth orbiting the sun. Compared to that giant orbit, the Earth is basically just a dot. So if we treat it like a particle, a single point that has mass but no size, we can suddenly figure out its entire path. It's a simple trick that makes impossible math possible. The second big trick is the rigid body. With this, we just assume that when we push on an object, it doesn't bend or stretch or squish at all. Now, in reality, everything gives a little bit. But this assumption is gold. It lets us design a massive skyscraper with confidence, because we can focus on the whole structure and not worry about the microscopic flex in every single beam. It's another super powerful simplification. So we've got the concepts, but what are the rules? Well, the entire world of mechanics is built on three fundamental laws cooked up by Isaac Newton. These are the non-negotiable rules of the game. The first law, the law of inertia, is really the heart and soul of statics. It basically says that things like to keep doing whatever they're already doing. An object that's sitting still wants to stay still. An object that's moving wants to keep moving. That is, unless some other force comes along and messes things up. That's the definition of equilibrium right there. So that brings us to the second law, which is the absolute core of dynamics. This law tells us what happens when the forces are not balanced. When you have an unbalanced push or pull on something, it's going to accelerate. And that whole relationship is wrapped up in that one famous, beautiful equation, F equals ma. And finally, we have the third law. For every action, there is an equal and opposite reaction. If you push on a wall, guess what? The wall pushes back on you with the exact same amount of force. It's a two-way street. These forces always come in pairs. And Newton didn't just stop with the laws of motion. He also gave us the law of gravity. That's the force of attraction between any two things that have mass. It's what holds the entire universe together, and it's what gives you weight. But, as you can see with this astronaut floating around, weight isn't exactly a constant thing. And this is such a key difference. Your mass, The amount of stuff you're made of is the same no matter where you go in the universe. But your weight is just the force of gravity pulling on that mass. Since gravity is different on the moon or way out in orbit, your weight changes too. You just calculate it by multiplying your mass by whatever the local acceleration of gravity, g, happens to be. Okay, so we've got the definitions, we've got the laws, but how do engineers actually go from all this theory to solving a real-world problem? Well, they use a very systematic process and some really essential tools. And I want you to listen to this, because the source material could not be clearer. It says that mastering this next skill isn't just helpful, it is an absolute requirement for solving any problem involving equilibrium, period. And this is it, the single most important tool in statics. It's called a free body diagram. What you do is you make a simple sketch of your object, you strip away everything else around it, and you just draw arrows for every single outside force that's acting on it. It magically transforms a complex, messy physical situation into a clean, solvable problem of balanced forces. And that free body diagram is step 2 in a bigger, very logical procedure. You start by really truly understanding the problem, then you draw your diagrams, you list out all the information you have, and only then at the very end do you apply the rules, like Newton's laws, to figure out what you don't know. It's a method, a system, and it works. So what's the big takeaway from all this? These concepts, from forces and equilibrium to those clever idealizations like particles and rigid bodies, they aren't just abstract ideas for a textbook. They are the essential toolkit that lets engineers analyze, predict, and ultimately design the physical world all around us. So I'll leave you with this final thought. Just look around you right now. Your chair, the table you're at, the building you're in, they're all in a perfect state of static equilibrium, with every single force in perfect balance. How many other things can you spot? It's pretty cool when you stop and think about it. Thanks for watching.